Alright, well hello physics students and welcome to this video lecture which is going to just kind of take us through the big ideas again with motion graphs, all of the stuff that we talked about in our first unit with motion graphs. It holds true with these rotational motion graphs, and then we're going to get into some application with these, being able to actually solve problems, creating motion graphs. Being able to document what's going on in a physical scenario using motion graphs. Okay, so first things first, this graphic right here should not be new to us. Okay, you should all have this in your notes, but just to reiterate, these are our three motion graphs, and it's important to remember what each of these motion graphs actually tells us. Okay, so from a position versus time graph, the slope of that gives us the velocity. Okay, from a velocity versus time graph, the slope of that gives us acceleration. And then if we go the other way, an acceleration versus time graph, if we take the area of that graph, that gives us the change in our velocity. And then from a velocity versus time graph, if we take that area, we get our change in position, we get our delta x. Now we can prove that by using units. Okay, so like if we were to take the slope of a position versus time graph, we would end up with meters per second, therefore it's velocity. Okay, so that's how we can prove to ourselves that this is what we're getting from each of these graphs. Now, if I can do this same sort of graphic for rotational motion graphs as well. I can say, you know, a angular displacement versus time graph, an angular velocity versus time graph, and then a angular acceleration versus time graph. Well, these are going to give me the same exact things that we see over here. So from a angular position versus time graph, the slope is going to give me my angular velocity. From an angular velocity versus time graph, the slope is going to give me my angular acceleration. All right, and same thing here. Okay, I take the area of an acceleration versus time graph, it's going to give me my change in angular velocity. And then finally, the area of an angular velocity graph is going to give me my angular displacement. Okay, so everything that we know holds true. Everything that we know about linear motion graphs holds true with rotational motion graphs. And that shouldn't be a surprise because everything that we've done so far with rotational motion is the same thing that we did in linear motion. We just have these new variables that we're working with. Okay, so now I want us to actually apply this to scenarios where we're given values and actually be able to create a motion graph and then solve a problem using that motion graph. So I have a simple scenario down here. We're looking at the second hand of a watch. Again, the second hand is the hand that counts the seconds. All right. So what we're told here is that the second hand rotates at a constant angular velocity of 0.105 radians per second. And then what we're trying to find is what the angular displacement in radians is after 90 seconds. So we have two valuable pieces of information here. The first is this right here. Okay, we have that angular velocity. And we also have time. So what I'm going to do here is I'm going to create an angular velocity versus time graph. Okay, so we know that the angular velocity is 0.105 radians per second, and we're looking at a time interval of 90 seconds. So that graph is pretty simple looking. It just looks like this. Now ultimately what we're trying to find is the angular displacement. So let's go up to our handy dandy chart here. So we have an angular velocity versus time graph. If I want the angular displacement, I need to take the area of this angular velocity graph. So all I need to do here is I just need to say, okay, well, this is clearly a rectangle, so I need to take base times height. So I'm going to take my 90 seconds times that angular velocity, notice that my seconds are going to cancel out here, and when we calculate that out, we end up with an angular displacement of 9.45 radians. Okay, so really simple example, just going through how we can actually create a motion graph based on values that were given and then solve for a particular unknown. Okay, now we could have solved this using an equation as well, but once again, I want us to really be comfortable using a variety of different methods to describe and analyze rotational motion. So the next slide is going to go through one more example of how we can do this. All right, so our next problem that we have here, we're looking at an old record player. Okay, so we're going old school here. So we're told that the old record player plays records at 4.71 radians per second. And now if the motor of that record player is turned off, it took the player 0.75 seconds to come to a complete stop. So our goal here is to find what the record player's angular acceleration is during that period of stopping. Okay, so once again, look at the two pieces of information that we have. We have an angular velocity and we have a time. Now, this angular velocity is actually, we're going to say that this is our initial velocity. And if it comes to a complete stop here, so I guess this is really our third piece of information, this would be our angular velocity final, which would be obviously 0. Okay, so with this information, we can create, again, an angular velocity versus time graph. Okay, so we're going to do that down here again. All right, put our units down. Okay, so now we'll mark off our initial angular velocity, which was 4.71. We'll mark off our time here, which was 0.75 seconds. And now our final velocity, again, is 0 radians per second. So really all we're doing here is we're just showing that this record player is slowing down in that positive direction. Okay, we don't really know the direction that this record player is moving, so we're just going to assume that it's in the positive direction. Okay, now we're trying to find the angular acceleration. So we have an angular velocity versus time graph. So to find the angular acceleration, we need to take the slope of this line that we have here. All right, so doing this then, our angular acceleration, remember slope is rise over run. So we always start from our second point. So what we're going to say here is that it's going to be our omega final minus omega initial divided by our t final minus t initial. Okay, so what that's going to look like then, we're going to have 0 minus 4.71 divided by 0.75 minus 0. Okay, so if we do that math, then we end up with a negative 6.28 radians per second squared. And it should make sense that this is negative, right? Because this is slowing down, and well, if you look at this line, it's a negative slope. Okay, so this value that we end up here, the negative value, should make sense to us. Okay, so the big takeaways here, everything that we know about motion graphs from our linear motion unit, all of those ideas hold true. I saw some really good things as you were working through that initial sheet yesterday, really focusing on the shapes, what the shapes of those graphs are telling you. But the main idea in this video lecture is that we can use these motion graphs, again, to actually analyze a scenario mathematically and to solve for particular variables using these motion graphs, understanding the things that they can give us. All right, so I hope you all have a great Easter break. We'll continue on with motion graphs, and then keep rocking and rolling in this unit after we get back. Take care, physics students.